Welcome back, everyone. Today our goal is to finish talking about section 4.3 on functions, which I know feels like we've been talking about forever now, because we've been talking about it basically forever now. Today's video doesn't really have any new content per se, but what I want to do is do some examples of how you prove things using the hypotheses that a function is one-to-one or onto, or how you get to the conclusions that something is one-to-one or onto, or in general, just how you write proofs about functions. So if you have a statement about every function rather than a particular function, we're going to go over what that looks like and do some examples. Okay, so here's a starting statement. So we've got two functions here, f from a to b, g from b to c, just like our setup for when we talked about function composition at the end of the last video. And basically, this exercise is going to be talking about what function composition does to one-to-one and onto. So in this first example, I'm going to ask, okay, we're going to prove that if both of these functions are already one-to-one, then so is their composition. And remember, the only composition that makes sense is g of f. F of g does not make sense if we have this set up in the way that we do. Now, I want to remind you, this is a for every statement. When I say if f and g are one-to-one, then so is g of f, this is implicitly a statement about all functions f and g. And so I have to make sure, when I'm proving this, I follow my general standards of how I prove for all statements. So my proof here is going to start with, well, suppose f and g are one-to-one. Now I'm going to consider g of f, and I'm going to write down the domain and codomain of g of f, just because that's going to be important. G of f takes in elements of A, and it outputs elements of C. Remember, the first thing I do is apply f, which takes in an element of A and spits out an element of B, but then I put that element of B into G, which then spits out an element of C. So that's why this is from A to C. So I want to show this is one-to-one. And so what does that mean I need to show? That means I need to show that if x and y are in A, and g of f of x equals g of f of y, then x equals y. All I've written down here is the definition of one-to-one with the appropriate domain, which is A, and I've written g of f because that's the function here I'm considering. So we know how to keep going now that we've written this down. So we're now going to suppose that x and y are in A, and g of f of x equals g of f of y. I'm going to spell that out just a bit more. By the way, if you've ever been curious what this little circle symbol is supposed to be, it's just supposed to be the O from the word of. So when we're reading it as g of f, this is really just meant to be a stand-in for the word of. But probably it makes a little more sense to write it out this way. Okay, so what am I meant to do with this information? Well, remember, I have some hypotheses. I know that f and g are one-to-one. And it may not look like it immediately, but if I actually look at this, g of f of x and g of f of y are equal. And so what does that tell me? Well, since g is one-to-one by assumption, that tells me f of x and f of y are equal. Let me just reiterate what's going on here. The fact that g is one-to-one, what does that mean? It means that if I put two things into g and I get back the same answer, then the two things I put into g were equal. In this case, the two things I'm putting into g happen to be f of x and f of y. And it doesn't matter that these things are actually functions applied to things, they're just things. And so when I put these two things into g, and I got back the same answer, that told me, because g was assumed to be one-to-one, that in fact those two things are the same. So I get that f of x is equal to f of y. So now what do we do? Well, now we actually get the more straightforward application of the definition of one-to-one. Namely, because f is one-to-one, and if I put x and y into f, I get the same output, that tells me that x and y are equal. But if you look holistically at what we've proved, what we've really proven is that if g of f of x equals g of f of y, then x equals y. That's exactly what we wanted to show, and so we've in fact shown that the composition of two one-to-one functions is one-to-one. Let's do this the other way. Let's prove that if f and g are both onto, then the composition is onto. Okay, just a reminder, remember that f here is going from a to b, and g here is going from b to c. So, to prove this, we're going to start, just like before, by assuming that we have these functions and that they're both onto. Okay, what is it I want to show? Well, remember again that g of f is going now from a to c, and what I want to show is that this function is onto. Namely, I want to show that for every c and c, there exists a and a, such that g of f of a equals little c. This is just the definition of onto. For every element of the codomain, there exists an element of the domain that maps to it. So how do I start this proof? Well, I need to show that this is true for every c and c, so I need to suppose, to start with, that I have a little c in big C. By the way, please note, I chose little c because it's an element of big C. You will confuse the ever-living daylights out of yourself and me if you call this little b because the definition of onto has a little b in it. You definitely don't want to do that, especially when there is a big B floating around inside this question. So now we have our little c in big C, and we want to now show that there's a little a in big A that will map to it. Unfortunately, my hypotheses don't let me do anything right away that involves big A. But the thing I do have hypotheses about is this map G. Namely, I know G is onto. And so, since G is onto, well, what does that tell me? Well, it tells me that there exists a little b in big B that maps to little c. Okay, so I've got my little b. Well, what can I do now? And, well, I'm almost priced into now doing the same thing with f. Because now little b, which was in the domain of G, is in the codomain of f, and so I can again say that because f is onto, there's something that maps to it. Now, in a fit of optimism, I'm going to call this element of A that maps to C little a, foreshadowing that I think this is the little a I'm looking for, but I certainly need to check that. So what I'm hoping turns out to be the case now is that if I take g of f of little a, it works out to be little c. Okay, well, what's f of a? F of a is b. And then g of b we chose so that it's c. So g of f of a is c. And then we're done. Because I've now shown that for an arbitrary little c in big C, there is a little a in big A, such that g of f of little a is c. Take a moment, read the definition, and make sure you understand what this definition is saying. So here's what's going on. I'm looking at the subsets of S, and I'm mapping each subset of S to an element of S. And the restriction is that that element of S that I'm mapping it to always has to be one of the elements that's in my set. And by in my set, I mean in my subset of S. Now, there's one time where that's definitely not possible, which is that if the subset I've chosen is the empty set, I can't map this to an element of the empty set. So I have sort of sloppily added this or A as the empty set on at the end here just to account for that. So let's start with just writing down a choice function for a set. So I'll choose the set 1, 2, 3. And so one way to write down a function is to just write down all of the elements of the domain of the function. Now note, I'm pointing at this S, but the S isn't the domain. The power set of S is the domain. So let's write down the power set of S. Remember, S has 3 elements, so its power set should have 2 cubed, which is 8 elements, and here we have them. So where do I send them? Well, I need to send 1, 2, 3 to an element of 1, 2, 3. I'll pick 2. I need to send 1, 2 to an element of 1, 2. 2 again sounds nice. I need to send 1, 3 to an element of 1, 3. Well, I can't use 2 again, so I guess I'll pick 3. Here I guess I'll pick 3. And here I actually don't have much of a choice. I have to send the set 1 to an element of the set 1, but there is only one. The same as here, and the same is true here. And where do I send the empty set? Well, remember the definition makes it so it doesn't matter where I send the empty set, so I guess I'll send it to 1. And so this whole tablet here, if you like, this defines a choice function for s equals 1, 2, 3. This is far from the only choice function for s equals 1, 2, 3, because I could just as easily, for example, have sent 1, 2, 3 to 3 instead of 2, and it would still work. It would still have been a choice function. So I made, well, as the name suggests, lots of choices for this function, and so there are lots of options. This is far from the only choice function. Next up, we're going to prove that every choice function is onto. Okay, so remember what that means. That means we want to show that for every little s in big S, that is in the codomain, because remember the codomain here is S, there exists a set A in the power set of S, that is in the domain, such that f of A is little s. Now, here's one example, but even for this set S, this is just one example. There are, in fact, 71 others. So I'm going to need to show this, that this function is onto, without referencing anything about a specific instance. Remember also, I'm not saying that this is true for just the set 1, 2, 3. I'm saying this is true for every set S. So, I guess we don't have a choice. Let's let little s be an element of big S, and f from the power set of S to S be a choice function. Now, I claim that there's one thing, even though there's lots of options, I claim there's one thing I know definitely maps to little s. Think about it for a moment. Pause the video if you have to. What is it I know has to map to little s? Well, the set S has to map to S. And so now, since by definition of choice function, well, the definition is that f of A is an element of A, so in this case that's saying f of A is an element of the singleton set S, well, there's only one element, and so we have f of A is S. And that, in fact, completes the proof that every choice function is onto. As usual, when showing something is onto, we're showing a for every there exists statement, and so there's just the small amount of cleverness we have to come up with because we have to go digging through our minds to figure out what A I'm supposed to choose. No one told us this is the A I'm supposed to choose. We had to figure that out. But I'll note if you had looked closely at this example, it would be pretty clear from looking at this piece of the table that looking at the sets 1, the set 2, and the set 3 would be a good idea, or indeed any singleton set would be a good idea to find something that maps to it. Okay, so here's another example. Let's now show that in fact no choice function is 1-to-1, at least assuming that the size of the set I'm looking at is at least 2. And I want to note, by the way, that we do make the obvious choice that infinity does count as being greater than or equal to 2. So this has a slightly different flavor from the previous examples, because now we're actually not showing something is 1-to-1, we're showing something is not 1-to-1. And so what does it mean to show that a function is not 1-to-1? Again, we should carefully write this down, as we want to show that there exist, let's say, a and b in the power set of S, such that f of a equals f of b. And don't forget, that's not all. We also need a is not equal to b. Remember, being 1-to-1 is the if-then statement. If f of a equals f of b, then a equals b. And so when we negate it, we get to keep the if part, because when you negate an if-then statement, you keep the if part, and then you negate the then part, and add an and between them. So this is our negation of 1-to-1. Again, this is made tricky by the fact that I don't have a specific function. So I really have to tax my brain and think about what could I choose to just guarantee that this has to be the case. And if you notice, the thing that should stand out to you in this question is the statement that the size of S is greater than or equal to 2. Why is this here? Well, it must be here because our proof is meant to involve writing down 2 elements. So I'm going to start my proof by saying, let x and y be elements of S. Now, I'm only doing that because I don't think this would be here in the statement of the problem if I wasn't supposed to do that. So, my function f doesn't actually take in x and y, it takes in sets. So, we might be tempted to think, okay, what happens if I take f of all of the sets that involve x and y? So, let's consider f of the set x, f of the set y, and f of the set xy. Do you see why this is going to prove to us that our function is not 1-to-1? If you don't see it yet, I really encourage you to pause and think about it. Here's what's happening. By the definition of a choice function, all 3 of these things are either x or y. In fact, this one is definitely x, this one is definitely y, and this one has to be x or y. But that's a problem because it means f of the set xy is always the same as f of the set x or f of the set y. Again, the reason why this is true is because what is a choice function? It's a function where I send each subset to one of its elements, and there are only 2 elements here. Now, what's really happening here is that this is a proof by cases, but this is an example where the cases are short enough that I would not break it out officially into a proof by cases. I would just say what I'm going to do. If this thing, f of the set xy, is x, I'm going to let a be the set x and b be the set xy. Those are going to be the a and the b and the thing I want to show. Otherwise, I'm going to let a be the set y and b be the set xy. And I've done that in both cases. F of a is equal to f of b, but a and b are not equal. And so that shows me that f is not 1-to-1. And so that completes the proof. A choice function is never 1-to-1. This is a useful trick, by the way. If you're reading a statement of a question, you should always read for any unusual hypotheses. Now, the fact that the size of S is at least 2 is not a really strong statement. In fact, it doesn't really rule out just about any set you'd ever consider. But it tells you where you should be looking, what rock you should look under. Namely, you should look under the rock of writing down 2 elements of S and seeing where that takes you. And this is a helpful problem-solving method, not just for this class, but for all future math classes that you're going to take. I want to note one particular exception to that, and that's just for this class. I will just about always include the assumption that a set is none-empty, and you should really not read anything into that. That's really just to stop you from ever having to think about what one of these definitions or implications or whatever would mean for the empty set, because no implication or statement about the empty set can possibly be interesting. So that is really just for you so that you can immediately put out of mind what's happening with the empty set. Don't read into the fact that that's telling you anything in particular about how to prove it. Okay, let's do one more example of this. Okay, so here we started with a function whose domain is just a set. We don't know anything about the set. I've just called it capital A. But the codomain is the real numbers. And that's significant because I know how to do lots of things with the real numbers. For example, I know how to subtract them, which is what I'm going to do in this particular example. I've used this function f from a to r to construct a new function, which I've called f with a squiggle on top of it. And that function does not, note, have the same domain as f. Now the domain of f squiggle is a cross a. And the way I make this function is that I take an ordered pair AB, both elements of big A, and I send it to f of little a minus f of little b. And note, because these things are both outputs of f, they're both real numbers, so this subtraction symbol makes sense. This is something you'll see quite often. You'll start with some function, and then you'll modify the function, or twist the function, or change the function around in some specific way to make a new function, and then you'll talk about the new function. So let's first prove that if f is onto, then f with a squiggle on top is also onto. To start the proof, we need to suppose all the if stuff, so we're going to suppose f from a to r is a function. So I'll just say f from a to r and f twiddle are as above. And f is onto. Okay, so what is it we want to show? We want to show that for every little r in big R, there's some element of a cross a, such that if you take f with a squiggle on top of that element of a cross a, you get r. Okay, this is just our same definition as onto as we always use, but applied now to f with a squiggle on top, which goes from a cross a to r and looks like this. Again here, the definition sort of tells us how we have to structure our proof. So I know that the statement I'm trying to show is that if little r is in big R, then there exists this thing. So I need to start by supposing that little r is in big R. Now, I kind of have to follow my nose a bit here, because I probably can't see all the way to the end of this problem from here. But there's a limited number of things I can do. I have an r in R. I know that f is onto. So here's one thing I can do. Well, since f is onto, I can find an element of a that maps to r. Now, again, I've written this down, and maybe I don't yet see how this is helpful, because I'm really looking to show something about f with a squiggle on top. But I can sort of imagine here, just sort of filling in the blank in my mind, if this was r, because f of a is r, and I want this whole thing to be r, what do I actually want? Well, it's not so hard to see. The thing I need in order for this to work out is I need this thing to be 0. Can I make f of b 0? Well, you bet I can, because f is onto, so definitely there's some element that maps to 0. Note, I've already decided that little a is the thing that maps to r, so I can't also call the thing that maps to 0 little a. I have to call it something else. I'll be uncreative. I'll call it little b. So once I've chosen this little a so that f of little a is r, and this little b so that f of little b is 0, then I can take f with a squiggle on top of ab, and that will be f of a minus f of b, which will be r minus 0, which will be r. And now I'm done, because now I've shown what I needed to, which is that there is some element in the domain of f with a squiggle on top that maps to r. So in the previous question, we were asked to show, hey, if I start with an onto f, show me that I always get an onto f with a squiggle on top. In this question, we're asked something that's kind of the opposite, which is show that no matter what happens, as long as the size of the domain of f is at least 2, then this function f with squiggle on top is never 1-to-1. Again, we can note not 1-to-1 means that I'm looking for 2 elements in where? 2 elements in A cross A, right? So there exist A, B, and C, D in A cross A such that AB is not equal to CD, where their outputs are equal to each other. By the way, note that this word never here, it sounds super strong, but it's just saying exactly the same thing as not. If the size of A is at least 2, then f squiggle is not 1-to-1. That's exactly what we're being asked to prove here. It is just a different way to say the same idea. Now, you might have noticed our little friend from earlier popped up again. Namely, this statement about the size of A being greater than or equal to 2. And you'll notice this pops up a lot when you're showing things are not 1-to-1, and that's because functions from singleton sets, if you think about it, are always 1-to-1 for really uninteresting reasons. And so it tends to be that when you're showing something's not 1-to-1, you're going to need to know that the set has size at least 2, and then you're going to be able to use writing down the 2 elements to do something. Some magic that you have to fill in yourself. So we're going to suppose here that f from A to R is a function, and the size of A is at least as big as 2. Again, it could be infinite, just has to be at least as big as 2. And now, since the size of A is at least as big as 2, there exist, let's call them 2 elements x and y in A with x not equal to y. It's not a lot, but it's all we have. 2 elements in A that are not equal to each other. I'll point out, by the way, at first it might seem like having a question where you're not given much in terms of hypotheses makes the question harder, but I think in a lot of ways it actually makes it easier, because if the thing you're being asked to prove is true, then if there's fewer hypotheses, there's fewer rocks to look under to try and get from where you start to where you have to finish. And so here, all I know about this A, like literally the only thing, is that it contains x and y. So somehow, in some way, that I don't see yet, I have to get from this x and this y to f with a squiggle on top is not 1-to-1. Now, you might remember that the definition of 1-to-1 or not 1-to-1 has a things not equal to it business, so that's maybe promising. But unfortunately, I can't plug x and y into f with the squiggle on top. I need to plug ordered pairs into that. And so now, let's briefly break for Scratchwork, and let's consider literally everything I could do with x and y. I could take this, I could take this, I could take this, and I could take this. Remember, f with a squiggle on top, it takes in 2 things, and so these are the only 4 ways that I could possibly write down one of x and y in the first slot and one of x and y in the second slot. Okay, so let me just write down what these are. This is f of x minus f of y. This is f of y minus f of x. Now you might pause and think, do I have any reason at all to suspect that f of x and minus f of y might be the same thing as f of y minus f of x? Because if it is, then I'm done. Unfortunately, as it happens, you think about it for a moment and then you realize that that's very unlikely to be true, because f of y minus f of x actually is the exact negative of f of x minus f of y. So it is very unlikely that these two elements are actually equal. So here, swing and a miss. We did not get anything. So let's hope that something falls out of this. If I take f with a squiggle on top of x comma x, that is by definition f of x minus f of x. Well, that I actually know what it is. That's 0. And now maybe the pieces of this click into place for you, because exactly the same thing happens for f of y comma y. And so this is exactly where I get my fact that f with a squiggle on top can't be 1-to-1 from. Namely, f with a squiggle on top of x comma x is always the same as f with a squiggle on top of y comma y, because it's always the case that both of those things are 0. So we can go back and finish the proof now. So I'm going to let AB be x comma x, and CD be y comma y. Then f with a squiggle on top of AB is f of x minus f of x is 0. And f with a squiggle on top of C comma D is f of y minus f of y, which is 0. So A, B, and C, D are different. And they're different because, remember, by assumption, x and y are different. But when I apply f with a squiggle on top to these two different things, I get the same answer. Namely, I get 0. And if I look back at what I wanted to show, it's exactly what I needed. Two elements of A cross A, which are different, but mapped to the same place. Okay, so I'm going to continue in the same universe. So f is still a function from A to the reals, and I'm going to define this particular subset of A cross A. So this is like A cross A, but what have I done? I've thrown out all of the entries where x and y are equal. So what's left is everything where x and y are different. And so now I'm going to define a new function. This one is going to be a variant on f with a squiggle on top. I'm going to call it f with a hat. And this is going to go from delta to r. And it's going to take the pair xy and send it to f of x minus f of y. Now, if you look back at it, the formula I gave for f with a squiggle on top and the formula I gave for this new f with a hat on top are exactly the same, except for unknown reasons I called them a and b here and I called them x and y here, but that has no relevance. So what actually makes these two different functions is that I changed the domain. Here, for f with a hat, I used the domain delta, which is a strict subset of A cross A, instead of using A cross A. So these are really different functions, because remember, a function is not just the way you describe it, it is also the domain and codomain. So here's the question. We want to prove that if f is 1-to-1, then f hat is not onto. Now, this is definitely the sort of question that you should look at and sort of make your eyes cross, because it seems really weird that somehow f being 1-to-1, because this really says is 1-to-1, not is not 1-to-1, somehow that is making f hat not onto. So I'm just going to start with Scratchwork, because I probably don't have any idea what is going on in this question to start with. So let's write out f is 1-to-1. What does that mean? I'm going to go ahead and replace this with its contrapositive, because in my set up here, I don't have x equal to y. I actually have x not equal to y, And I would kind of prefer it if this definition looked as much like the thing I'm going to have to deal with as possible. Okay, so the contrapositive here is that if x and y are in A and x is not equal to y, then f of x is not equal to f of y. Now, as you start to piece this together, you might notice some commonalities. So I've got an f of x and an f of y, and I've got an f of x minus f of y. Well, I can turn this into an f of x minus f of y. All I would have to do is subtract f of y from the right-hand side. So this thing actually means the same thing as f of x minus f of y is not 0. Take a minute, if you don't see it right away, and think about how is this mess of rewriting that we've done, how is this going to let us show the thing we want, which is that f hat is not onto? So here's what's going on. This thing, this f of x minus f of y, that's the output of f hat. But basically what I've just wound through here as I've written all of this out is that under the assumptions we have, f hat never takes the value 0. And so, in fact, we're going to prove, without really knowing anything about f, or anything about delta, or anything of that sort of thing, we're going to prove that this function f hat can't possibly take the value 0. So let me write this up now that we've done the Scratchwork and we see how the pieces are connected. Let's actually write down the proof. By the way, this is a phrase that you might want to start internalizing, that if the setup of the problem is complicated, you often in your proof will suppose things are as given, which just means I'm not copying the whole question. You can read the question. I'm just going to sort of jump in with how things are defined. And note, all I'm doing here is saying, well, the question actively defined an f hat and a delta, so I'm just saying, okay, take that definition of f hat and that definition of delta. Here, the question is weird enough that we need to tell the reader what's going on right up front. Namely, the first thing we're saying here after we do the setup is, okay, this is what I'm going to show you. I'm going to show you that every input here does not map to 0. And once I've shown you that, I've shown you this thing is not onto. Now, this tells the reader what they're expecting you to do. Because if you don't tell them this up front, then they're just sort of watching you do things. And there is nothing worse than just sort of watching a proof do things without any idea where it's going. And it's really hard to sort of put the pieces together. But here we're just going to say up front, this is the thing I'm going to prove, and as soon as I prove this, I've shown f hat is not onto. So, now of course I'm obligated to actually prove the claim, I don't get to just claim it. So, let's let xy be in delta. So by definition, x and y are in A, and x is not equal to y. Now I'll go ahead and say, since f is 1 to 1, f of x is not equal to f of y. Now, consider f hat of x comma y. Well, what is it? It's f of x minus f of y. But, since f of x is not equal to f of y, that tells us that f of x minus f of y is not 0. And so f hat of xy is not 0. And that's what we needed to prove. And that completes our proof. I think as you look through the homework, you'll see that the questions I've chosen today were inspired by, in a lot of ways, the questions I've asked you to do on the homework. So you may want to come back and review some of these proofs as you go through the homework and find new things that you're being asked to prove. But I'm going to leave it there for now. I'll see you next time.